I would like to hand over to our first speaker, Josefin.
Thank you, Jacob. Trying to unmute and talk at the same time is harder than you can think. So yeah, today I will talk about model evaluation using production data, and hopefully this is something that you can all learn something about. We have several models in production, and I know that multiple people has been interested in hearing how we evaluate those. So this is what I'm going to talk about today. First, just wanted to touch briefly about who I am. So I graduated Chalmers. I took my master's in computer science, algorithms, languages, and logic, and I finished my studies at the end of 2017, when I also started Record a Future as a software engineer. And about that time, I also joined the MLDS Gothenburg meetup organization. And I'm still at Record a Future today. I'm also a co-founder and board member of GAIA, which I'm sure all of you have heard about by now, and I am helping out with arranging the conference and also the meetups. So also touch briefly on what Record a Future is, because I think maybe not all of you know that. So in my own words, Record a Future is a security intelligence company that provides information about stuff that happens on the internet. And this is to help our clients stay safe. And stay safe is a really broad expression. So I have some examples of use cases where we help our users. So it could be, for example, to find leaked credentials from people within our users' organizations. Also keep track of stolen credit cards or gift cards that are for sale for, in example, underground forums. We also support vulnerability patching and prioritization, or vulnerability patching prioritization. And this is something that Mats will talk more about in the second talk of this meetup. We also keep track of command and control servers and help our clients find out if they have any such network activity within their networks. Register phishing websites that are targeting the organizations, campaigns, and protests against them, like organizations or companies, and also help their employees stay safe by keeping track of terrorist attacks or violence in areas where they have offices or storage. So yeah. So the Record a Future platform, this is just like a high overview of what our pipeline looks like. We have collection from various sources. I think we have more than 800,000 sources where we collect data from. Some of them are structured data, like DNS information and certificate and domain registrations. But we also have a really, really wide collection of unstructured data. So that can be tweets and forums and text in various languages. And then we process them in our natural language processing pipeline, which I will talk more about later. And we pull them into what we call the security intelligence graph, which is basically multiple Elasticsearch indexes. And then we use that information either to create something which we call risk scores and predictions. And we also go in and do manual creations, of course, of that data. And then we deliver the information through various ways. So through APIs or integrations or a UI portal. So the part where I'm gonna talk more about is a part in our natural language processing pipeline, which is called event detection. And Mats is going to talk more about predictions that are made based on whatever information that we've found previously in the pipeline. So just to also create some common grounds, some of the lingo that we may use, we have documents coming into the pipeline, as I said. So for unstructured data, we get about 40 million documents a day. And these documents we divide into something that we call references. And a reference is basically a sentence within a document that is describing something that is happening that we think may be of interest. And in these references, we extract entities. So entities are the nouns in those sentences. And it can be things like, countries, persons, not like individuals that are not like, we don't care about you guys. We care about people that are highly famous, like Donald Trump, and so on. And we also keep track of like IP addresses and malwares and so on. And then we cluster these references into something that we call events. An event is something that could be of interest and that can help us understand what is actually happening. So in this case, these three references all represent a cyber attack event. And then we can look at the aggregations of these events and entities and references in our system and create something that we call signals. And we use these signals to produce risk scores, as I mentioned earlier. And they are like really helpful for people to know, what's trending, if something is being talked about, and if that is the case, how much and where. And this hopefully gives our users some context on what is happening in the world and what they should spend more time looking into to reduce risk. So for the event classifications, so as I said, we get documents into our pipeline and we divide it into references. And then we send these references to microservices where we run our machine learning models. And we let that model make a prediction. So in this case, we have a model for each event type. And the model returns basically a probability of how probable it is that that event is of a certain type. So in this case, we have a 0.89 probability of this event being a cyber attack. And then we index that information and produce signals and so on, as I said. So today I'm gonna talk about or like go into deeper into how we evaluate our models. And when we do that, we look at a certain list of properties that we would like to see. So for example, we want to know the expected precision in production. We also want to get a notion of the recall that we receive in production and the volumes, like how many events would we produce per day of a certain event type. And this is interesting because a lot of our users have alerts on events. So that would give us a better understanding of how many alerts they would receive from Recorded Future if they have a certain query set up. And then, of course, we want to identify biases and weird false positives because those are sometimes embarrassing. The weird false positives, that is, the biases we want to identify because I think you all get it. It's bad, and we may introduce biases that we are not aware of, and we really want to give as good of a picture of the real world as possible. And then we want to help with determining thresholds. That is, above what prediction rate do we want to actually produce positives. And we want to do this with fast iterations, and we want to have reproducible results, and we want to have continuous measurements. And what we've learned is that you can't have it all. But we've like established two different ways of going at it that at least covers most of it. So that is pre-production evaluation and something that we're calling post-production evaluation. So let's start with the before deploy phase and how we do pre-production evaluation. Or no, sorry, I will start with the hold-up method because I think that is something that you're all aware of. So the hold-up method is when you hold out a part of your training data set and you test how well the model has generalized to the problem by running the model on that set of data that you have not trained the model. And this is probably the most usual way to go at it and to get precision and recall metrics. However, in our case, our test data is a highly curated set. And that is because we have a really skewed data sets in real life. So I think if we would take a true random sample of the distribution, we will get about one positive in a million predictions or in a million instances, which doesn't really go that well with most of the model architectures that are out there. So what we've done is that we've sampled and curated our training data, not only the positive samples, but also the negative ones. So because that is the case, we don't really get a good measurement of how our model would actually do in production. So the top three ones I crossed out here because they are not fulfilled. However, this allows us to do fast iterations and we do get reproducible results, which is really good. We can also assume that the hold-up method would give us, if the hold-up method would give us a precision that is high, but not high enough, then we can be quite certain that it will be definitely not high enough in production. So that's good. So another approach, which I think is quite common, is to do a dark deploy before release. And that is when you put the model into production and you run it through the pipeline, but you're not producing any results to the clients or to the users. And this is actually quite good. We can get a good estimate of precision. We can't really get a good estimate of recall because we don't have a way to measure all the negatives because there's so many of them. But the volumes, the biases, and the thresholds we get help with determining. And we also get continuous measurements. However, we don't get reproducible results because they are running on a live pipeline. And the biggest problem here is actually that it's really hard to do fast iterations. So as I said, we have about 40 million documents a day going into our pipeline. And for some of our models, we have like one positive example per a million documents. So that would give us 40 positive results in a day if we're lucky. That's actually quite a high number. Usually we'll have to let them run for a week or two before we can feel confident. And that is way too long time for us to be able to know. We want to iterate faster, basically. So for the pre-production evaluation, we've come up with a solution which we think works pretty well for us, actually. So what we do is that we pull out a huge sample from production, and then we run our models in parallel on that sample. And that solves a lot of our problems. And I will go through how we do this in more detail. So as I said, we have our production Elasticsearch index. So we pull out a random sample and we store it in S3 buckets. And then we have our process, which we call production evaluation, which then takes this shuffle the dataset or this random sample. In this case, it's 10 million random sampled documents or references from production. And we run our model on those 10 million not all of them at the same time, but we start running our models in parallel on these 10 million instances. And of course, we have defined which artifacts to use. And then we have defined a sample size. So in this case, we have said that we want to run the model until we get 150 positive references or positive predictions. And we've defined a positive prediction in this case as everything that is predicted above 0.7 probability. And then we pull it into our annotation database, where we have an annotation service which allows annotators. It could be us, it could be other people within the company, it could be external people, depending on the problem. In this case, it's usually the developer that does the annotation. And when the annotation is done, we can compare the annotated references or instances with whatever the model has predicted, and we get a nice summary of how well the model would do on production data. So in this case, if we would have set the threshold, for example, to 0.73, we would get a precision around 90% in production, which is good. We also get out the true positives and the false positives, and we store the instances, of course, so we can look through them. And this is where we can identify weird biases and also false positives, so that we can go back and make any adjustments to the model in order to tackle them. And then we get something that we call positive prediction rate. And this helps us determine something which we call a relative recall, which has also helped us a lot. And that is a way for us to compare how many positives we can get per each model. And we can, like, if we want to increase the recall, we take the model with higher positive prediction rates. Yeah. So some learnings and takeaways from this. This actually works really good for us. It has saved us a lot of time. So to run one of these jobs basically takes about an hour, I would say, instead of a week, which it does when we do a dark deploy in most cases. I want to say that, like, the hold up method may not be enough. It's easy, it's what most people use, but for us it really didn't work. And this is just one way that you can go at it, but experiment with other ways to test models. Also, as I said, waiting is boring. Fast iterations are really valuable. And this is how we've done it. And this is fast enough for us for now, at least. Also want to put some emphasis on the more the merrier, that the data volume is crucial. The more you test, the more data you test your model on, the more certain you can be that you're good enough or not good enough. And also don't overwork it. Good enough is enough. You can improve later in most cases. That may not be the case if you work in Medicare or something like that. So let's look at the after deploy section. So here we created something we call post-production evaluation. And as you see, this is really similar to the dark deploy. The difference is that we're now actually producing data that our customers can see, or our clients, or our users. And here we can get a hold of those continuous measurements. And we get the sense of, again, the volumes. We get some weird biases and also weird false positives. And it can also help us determining thresholds, like if we want to increase or decrease the threshold, then we can get a sense of how much or how that would affect the precision of the model. So looking at our pipeline, we get documents, we send them to our models, and from our models we pull samples live, and we store them in this database. And then we run our post-production evaluation process, which pulls out a set of samples. So in this case, we defined like an evaluation job through configurations. So here we have a configuration or an evaluation job for our cyber attack classifier in Japanese. And we've defined this thing called buckets, which helps us determine, for example, or more specifically, it helps us determine the evaluation metrics for a certain threshold. So here we look at everything that is detected or everything that is predicted to be above 80 in probability of being a cyber attack. And we can also determine other filters. I will I will go through some of them later, but here is like the filters also contains the probability interval for which we want to do the evaluation. Yeah, so here we pull out samples that are between that are above 0.8 in probability of being a cyber attack, and then we've defined a quantity. So in this case, we've said that okay, we want to in each of these evaluation jobs, we want to look at 100 positive predictions. We use the same annotation database and annotation service. And in this case, it's not the people within the team that actually does the annotation, but we have other people within the company, which are very helpful with us and are doing the annotations. And they get a Slack notification when there is a new annotation job that they can look through. And then when they're done, we compare the annotations to the model's predictions, and we get and calculate some results and metrics, which we store, in this case, in an influx database. And we get these really nice continuous measurements of the precision of our models in production. And we also get a Slack notification when a new evaluation is done. And this has worked really good for us. We do this for this specific model. We do this evaluation once a week. And it really helps us feel confident in our models. We also look through these measurements. And the ones that we feel need work on, we lift that to our product manager and like tell him that, hey, there's a problem here. Maybe we should look at it. Maybe we should plan putting in some time into improving this. And this really gives us leverage to that statement. I can also tell you that there's sometimes, the good thing here is that it's the case, it happened earlier this spring, for example, that a model all of a sudden started to sink in precision. We saw that the precision decreased a lot. And since we have people that are actually looking at the data, we can talk to them and ask them if they're seeing something different in the data. So in that case, it was the Japanese cyber attack. And they said, well, we're seeing a lot of false positives containing the mention of coronavirus. And it's not that weird that the model believes that a lot of talking about viruses are also talking about cyber attacks. However, in this case, it's not something that we are interested when it comes to cyber attacks. And we got to use another part of the filter, which allows us to say that anything containing these specific strings should never be predicted or allowed to be positive for that event type. And this allows us to act fast. And during the meantime, we can lower the amounts of false positives, and then we can go back and retrain our model without having to spam our users while we do that work and going through the whole process of pre-production evaluation and so on. So this has been very helpful for us also, actually. So some learnings and takeaways from post-production evaluation. Humans are good and bad. It's really good to have them help us out. We have to spend a lot of time on defining the problem and writing annotation guidelines and answering questions. But that time is time well spent, I would say. And it's also not always the case that they come to us when they start seeing things. So we have these continuous meetings with them where we ask them questions to see if there's something that we could improve with the models that they see based on what they see in the data. We also learned that metrics are very valuable, but if you don't look at them, they don't really do that much for you. So we have also regular meetings just looking at the metrics and discussing them. And as I said, lifting up if we're seeing anything that is problematic and discussing it. And like we can make adjustments or we can choose not to, but we've learned that it should be an active decision. We need to keep control of our models and be aware of how they're doing. And also, we learned that it's very important to be humble. This has taken a lot of time for us, not just to implement it, but just to define which process works for us and all the people that are involved. And of course, nothing is perfect, especially not right away. So the last thing that I want to just briefly mention is process monitoring. Hopefully this is something that all of you do that has models in production, but I just wanted to touch briefly on it. Maybe someone could get an idea or see the value in it. So we do monitoring of both our microservices, like the services where our models are running, but also from the calling service. And we basically measure everything. We time everything. We measure the amounts of failed requests, successful requests, how many documents are, not complete with all the information that they should have for us to be able to do a prediction based on it, like the information about the entities and so on. And we store everything in Influx database again, which is a time series database. And then it gives us these really nice metrics which we can look at in Grafana. And Grafana also have an alerting feature, so we can or we are getting alerts when something is behaving, abnormally weird. If we get a lot of fails from a certain model, which we did also at some point, which at least made us aware of it, so we could go in and we actually discovered that we had a memory leak. So that has also been very helpful. We also use something called Sensu, which is a process monitoring service, which notifies us if there's any fatal errors. So, for example, if there's something wrong with like model artifact, if someone has accidentally removed it from the S3 bucket where it's stored, or if we've done something with, updated a TensorFlow version and all of a sudden the process won't start. So that also works really good for us. And of course, we have an ELK stack, Elasticsearch log stack in Kibana, which helps us look at all the logs from all the processes, which is really valuable when troubleshooting. Some final key takeaways or summary. Experiment with other ways to test your models except the holdout method. Don't overwork it and feel confident that it will be good enough. Follow up on your metrics and monitor everything. And that's it for me. And I saw that we had at least a couple of questions.
Yeah, thank you, Josefin. So we have two questions from Jesper.
Yep.
And for you who missed the beginning, you can ask questions using the Q&A button at the bottom of the UI. So ask questions there, and then we will ask them to the speaker at the end of each presentation. So first question, what about false negatives? Isn't there a big risk of enforcing selection bias?
Yeah, so as I said, like false negatives are really hard for us to handle since we have so huge data sets. And a big risk of enforcing selection bias. I mean, yeah, it is. We don't really have any better ways to work with it. If you have any suggestions, I'm eager to hear them. Maybe we can talk more about that afterwards. Jesper.
Sure, Jesper is willing to share all his ideas at a later
Yeah, hopefully.
time. Second question, do you couple your model's precision recall with some business metric? For example, do you know if or how precision and recall actually correlate with your business goals?
Right now, we don't have any tightly coupled metrics. We are working on it though. I think like we have business goals in that are defined not really on such a low level, which makes it a bit hard to see like direct connections between them, basically. But yeah, we are working on it. We have, yeah, our business metrics are on a much higher level. But we do have metrics on that we want to not to send more than a certain amount of false alerts for certain use cases and so on. And in those cases, our precision and volume metrics that I talked about earlier really helps us know if we are on the right way or if we are way off or if we are successful there.
Okay, that was all the questions we had this far. So I guess we hand over to Mats.
Just unmute as well. That's a problem. So let's see. I'm going to share my screen. So do you see now?
Yeah, it looks good.
Okay, thanks. Somebody can confirm. Everybody else is muted, of course. So I'm going to talk about the vulnerability exploit risk. It's one of these things that Josefin referred to when we're talking about enriching the data, so to speak. So this is my brief outline for some personal stuff. Who am I? And then again, going into the data pipeline briefly, and then explain what cyber vulnerabilities are, how our data looks like, modeling and results, and then it's tricky, but it's a bit special to do validation of predictions. So I'm just going to touch briefly on that. So my personal background is I was a Chalmers, engineering mathematics, 99, and then a PhD in mathematical statistics, postdoc, and then front office Chalmers Center for 7 years. Then after 18 years at the Chalmers campus, I thought that it was time to leave the campus. So then I started at AstraZeneca, worked there for 4 years as a global product statistician for a compound. And then when the autonomous drive bus came along during 2016-17, I just had to join Zenuity when that started. So I was with Zenuity from start for 2.5 years. I was working with probe source maps. This is where you take camera images or camera detections from all the cars that are driving around, and then you make maps out of that. And then in 19, or roughly a year ago, I started at Recorded Future. I was actually a brief stint when I was at Fraunhofer. I got to learn Recorded Future back in 2012, when it was quite recently started. So then I thought that when it's time to leave Zenuity, I asked if they had a job at Recorded Future, and turned out that I got a job there. So I'm doing called predictive analytics. It's a bit of a buzzword, of course, but it's basically an analysis and enrichment of data. So here's the pipeline again. So things are coming in. Let's see, I get a pointer. So here was the thing that Josefin talked about, where you have all the unstructured data, basically text data, fragments, sentences, documents, and then you have the natural language processing pipeline, which take out all the entities. What are they talking about here, and who's talking about who, and at which time point do we talk about this? And then where I work is then in this area here, taking in all the things that have already been done, so to speak. The hardest part, I got the nicely structured data here, which I can look at. Of course, sometimes you have to go back anyway, of course, to the fragments, to the actual sentences, but it's basically more structured data where I work. So just give you a brief idea of what's going on here. Josefin also did this, but these are typically this unstructured data. You have a text from Twitter in this case here. The only thing we know then is publication date and the source Twitter, and then you have a fragment here and so forth. Here is a blog post called Krebs on Security, which is the trusted source, so to speak, for many things related to IT security. Then you have something from dark web here as well. You have actually a session of hijacking Facebook for beginners. That's something interesting. I've just blanked out some things here. If there's somebody from that has written this, I shouldn't say everything what kind of data we have. So it goes through the natural language processing, and then what you get is this, the very rich JSON structure. So from one sentence here, this is what you get. So what made Recorded Future special in the beginning, this is the core about Recorded Future is actually be able to time tag things. So here you have something saying that it's actually not in this sentence, but it's earlier this month was the time fragment in this in the neighboring sentence here, and then you know the publication date, and then what does that mean in this context? And since it's published there, it should mean a month. So we have a precision of month there. So of course it should be, you know, from the 1st to 11th of August, but it's we're not too picky here. So this is the key thing. You cannot Google these kind of things. You cannot Google what's going to happen in Gothenburg next week. You have to have then time tagged information. That is the core behind Recorded Future. And then after a couple of years, Recorded Future focused more on cybersecurity than this more of a general Google advanced, so to speak. So cyber intelligence or cybersecurity, then there is a key thing called cyber vulnerabilities. That's basically, you could say that's bugs in the software that you have. But it's more related to maybe your vulnerability where you can get access to or going into SharePoint site or something like that. It could be very specific, and so it's basically bugs that you can use for getting access to systems in various ways. And it's about these numbers from 2014, between 8,000 to 18,000 software vulnerabilities were reported to this national vulnerability database. That's in US, as everything with national stands for, right? So then it's been giving a CVE identifier. So that's a common vulnerability and exposures. That's kind of a nomenclature here. You have to remember that because I'm going to refer to CVEs later on. I don't want to write vulnerabilities all the time. And it gets a score about how dangerous is this. this vulnerability. And these vulnerabilities, there is a strategy on openness here. So Microsoft they have a patch Tuesday. So every second Tuesday of the month, they are then releasing patches and also information on the vulnerabilities that they have on their systems or their products. And it's quite open on what this means. So it brings, for the IT security and for the community, they can learn from this openness, but it also opens up, of course, for being able to hack, maybe, because you're telling exactly or quite well what system, what version is affected, and what you can do. Not maybe exactly, because then you have exploit code. We're going to go into that. And about 1% to 4% of the vulnerabilities, this we don't know, of course, how many are actually exploited. And exploited means that they're weaponized, and they're used in malware. And this typically happens within a couple of months from the disclosure, if it's ever going to be then exploited. And this is, of course, it's speculative. This is basically the common belief in the society of cybersecurity, because we cannot know all the exploits. There are very many vulnerabilities that are exploited without anybody knowing about it, of course. So what this means that IT security, they have to patch these things. So typically when you get a patch, as well as the patch Tuesday, for example, that Microsoft has, you have a patch so you can fix the system, basically. But this is not that easy on big companies. You have to close down, maybe we're going to close down all the systems with the SharePoint for 6 hours during Saturday, and please don't do anything then. And that might have severe consequences for shutting down systems like that. So you have to prioritize. You have to really patch the things you need to patch. You don't patch everything, basically. You have to prioritize here. So if we would have a tool that then could predict, or based on what is said on the internet, so to speak, in the dark web everywhere, what it's talked about a particular vulnerability, can that help us then prioritize? So that's what I'm going to talk about. So this is the cyber vulnerability threat view that we have, and as you can imagine, it's quite red everywhere, right? There is the top risk is 99, and you have this risk here, for example, is just way all over the place. And the funny thing that this CVE number, that was the enumeration, and there were quite old ones here. The first 4 numbers, they indicate the year that it was released or disclosed. So there are still old bugs, so to speak, floating around, because they wouldn't do exploits on things that are not used anywhere. But I guess you also know things, old components that you still use, maybe at home, but also at the company. So what this is the signal. Then we talked about, this is the intelligence score. So if you want to know something about a vulnerability or an IP address or a domain, you get this summarization. This is the signaling that Josefin talked about. So it's a summarization of everything we know right now about a certain vulnerability in this case. And you get a risk score in the range 0 to 99. This risk score is basically that, with a few exceptions, those are rule-based. And they're summarizing what we know right now. They don't, if there are any textual references, just talk about something, it's not reflected in this risk score. It can never go up above 80, which is the critical area, so to speak. It is a critical risk that you can never do without technical evidence in our current pipeline. But we want to have, even though it's crowded at the top, typically a cyber intelligence person, they have a list, of course, with the vulnerabilities that affect their tech stack. And they're, of course, watching only that. So they don't look at this huge, let's see, I'm going to get the pointer back. Where is it? Sorry. They don't look at all this huge matrix here that you see in the left bottom here. They have a very specific stack. Let's see. So this is the vulnerability exploit risk. This is the kind of timeline for the vulnerabilities. You get, here is the key when it's disclosed. That's when you get the entry in the NVD. You get a CVE number, so to speak. There is sometimes you get the vendor might expose, for example, Microsoft. They actually do a patch before they send in all the information to the NVD. So that's called pre-NVD time. So there's something going on before you get all the information on NVD. But then there is a part here where you get rumors. There's a lot of talk about it on GitHub, Twitter, dark web about this vulnerability. And some are trusted that, it could be Google Project Zero or Zero Day Today, which is they talk about exploits that they know are being done right now, or then exploiting vulnerabilities, or that they know. But this is, and then you get a verified exploit. This is the technical evidence when this has been caught in the virus scan. There is knowledge behind that this particular malware then uses a particular vulnerability that then is exploited in order to get access to the system. That we know. That when that happens, that technical evidence, we get that availability. But we want to know, what we want to do basically is use all these things. Can we give some kind of hint before this happens? Because then it might be too late. Then this has gone quite a long time before that has been reverse engineering, getting a scan, so it gets caught in a scan as well, on like a virus scan then. So this might take a long time. So you want to be able to then use this in order to predict, so to speak, whether this is going to happen or not. So given what has been set up about a certain vulnerability up until today, what is the probability that it will be exploited in the future? And this exploited in the future means then sometimes, of course, we're just verifying. We see in the text that it seems like it is being exploited, but it's this that is verified to be exploited. So we can give some kind of hint of, okay, we're summarizing what's being said on the internet right now about this certain vulnerability. So the idea then is we got a bunch of historic data here. We got all the references talking about a certain vulnerability, and we have these verified exploit for then a couple of roughly 1,000 of the vulnerabilities that we then have confirmed these have been found in virus scans. But we actually didn't know the time point when this happened, when we did this modeling. So we have to then, if it included, if the fragments that we're analyzing, if that included something that was a verification of the exploit, then we had to remove that manually or finding ways to remove that before we trained it. So the idea here is to take the first X number of days. We're going to take 60 days of the lifetime of the vulnerability and build a classifier basically based on that. Most of the stuff talking about vulnerability is being done in the beginning. When everybody's talking about it, when it's news, when it's fresh and new, then that's when you get most of the information. So just a brief discussion on the precision recall. The business case is balanced then between high recall, that we can say, okay, we are going to find all the exploits that is going to happen. We will find that. If you're going to make that claim, then you need to have high recall, right? But if we're going to say instead, if we say that something is going to be bad, this is a high predictive score of being exploited, and you should trust us. Please patch as soon as possible. Then of course we're aiming for high precision, and the thing is, with IT security personnel, they don't have time to patch everything. As I said, they want high precision. So if they can find some more indication of this is going bad, and then we can tell them, if we say this is going bad, please patch, then they're going to trust us. That's a business case here. So if there anytime a balance between this, then we're going to aim for high precision. And just a brief talk about this CVSS score. This is a common vulnerability scoring system, and it's issued by the National Vulnerability Database. So they basically score all the vulnerabilities, but it's more of a they measure the ease of exploit, if you can do it remotely, or if you need to have sudo rights and stuff like that, and the potential impact on the computer system. So it's more on the potential danger that they measure with the CVSS. But in some companies, you actually have a rule that everything which has the highest CVSS score, you have to patch. For example, many US governmental agencies, they have this rule. So then this basically, you see that if you're going to do that, you have a precision of 9.5% and a recall of 14.9. So it's really bad. You don't want to do that. It's going to be turning into a wild goose chase. So we need to have something more than just a CVSS score. And then what we're going to do then is take the temperature, so to speak, of each vulnerability and using data collected by the RF pipeline to make that assessment. So what we're going to do now is, as I said, we're going to take the first 6 days out of this for each vulnerability when it was disclosed, and actually we're going to take 7 days before as well, because we have this pre-MBD time when typically things are happening before as well. If something is mentioned about it. I'm going to take out from this fragment, we're going to use the pipeline that Josefin talked about, where you have all the entities, all the nouns, and we're also going to take out the document language and source type. Quite arbitrary, these ones, but we believe that the document language and source type is typically good to have. For example, if it's mainstream media, if it's social media, if it's or if it's dark web. Those are quite different in nature. Language is of course speculative, but Swedish, Russian, and I think Swedish is in the top 4 actually on being the dangerous language in the regarding exploits. But it's of course Korean and Chinese as well. So number of references, number of sentences mentioned about the CV, this goes skyrocket. So we have disclosure date here. This is a high profile CV, as we call them, when something they're very, everybody likes to talk about them because there might be some special things about them. So, but it's typically initial search of textual references for the first month. And this is where you want to take out, here is actually the disclosure fragment in this case. So that's not that exciting, but what you get is the entities here. This is actually the entity for the vulnerability itself. And this is, I think, for the vulnerability NVD. So it's when this one, and that is actually just a vulnerability. So it's not no information here, of course, but we get that out, and also the language and so. Let's see, yeah, entities here. So these are, we do that, we get counters for every day. You see that this particular, oh, sorry, why did that happen? Strange. Yep. So these are these counters of all these entities for every day. So the disclosure date was the 1st of July. Get something before, and then 66 references, 27, 165. You know, then it just explodes, as this graph also indicates. These are the kind of text or example fragments that you have. And you see that threat actors have already been starting exploiting this one. And that's released 3 days after. And you have, we've seen a lot of proof of concept code for this vulnerability. And these kind of sentences, you want to capture this, right? You don't get that summarization without the recorded future, I was about to say, but that's what you're going to do, to get some kind of risk score out of all these sentences. So it says there's a lot of claims about proof of concept. And of course, the sources are typically Twitter here. They are competing, all the security experts, they tweet a lot about these things in the beginning. But there are some trusted sources, or sources which are more trusted than others. So what we have as data are then these exploited in the wild, what you call them. These are then the technical evidence. We have barely 1,000 of these in this period 2014 to 19. The reason 2014 is because that's when Record the Future is starting with the cybersecurity. So we have a lot more data, actually, a much more complete picture of everything related to cybersecurity from 2014. And 2019 is because when we need to save 2020 for validation. And also because I trained this model in the beginning of the year. So, and then of course we need another, those which are not exploited. That's not as, you cannot tell for sure, of course, that something is not exploited, but we ended up after cleaning and so forth, but this we got roughly 8,000. So we have roughly 10,000 CVs here to train our system. And we then do this, taking out features, which are these counters, everything. That becomes a lot of entities that are mentioned. It's a couple of 100,000, of course, because they could talk about anything in these fragments, basically. Not anything, but very many things. So we just kept those features, which are at least in 20 of the CVs. And then you actually go down to 638 features, which is quite, you know, that's probable or very reasonable to handle, right? It's not a big data problem. So, and we actually collapse all of this and just get a bag of terms. So every vulnerability just get a bag of terms of which entity was it talked about here. And then the idea is for this, we use the random forest. And the reason for that is basically there is this notion about decision trees typically work well in imbalanced classes. Yeah, we have a bit of an imbalance here. About 10% are actually exploited in this data set. That's also what you can see in reality. The most important thing is actually that I like to use random forest. That's my first go-to model. And I think it's reasonable not to have a deep neural network simply due to we have so little data actually. The drawback is, of course, that this is a black box model. So these are the example, the feature vectors. So get this. It looks like rubbish for you, of course, but all these are entity codes then, and of course English. So here we have 992 references in English, and this is Chinese, traditional, Spanish, Japanese, French, Italian, and so forth. And you got some that you can read what they are. And you see that we have no time dependence. This is a pure classifier. It's a very simple model actually. One bag of turn per CV, collapsing everything, which of course has its drawbacks. We cannot distinguish everything. So after training, well, the precision on this on the test set, taking out 20% and doing cross validation, of course, when we were tuning parameters and so forth. But we ended up with a precision of 85% and a recall of 51, which is, I would say, fairly good for this example. It's in the, you know, in the literature about exploit prediction. This is quite good. But this is not reality. We have to go back to this is on the training and test data set, which is not the same thing as how this will perform in reality. So, and these are the feature importance that you get out from the random forest. And when I started at Record the Future, somebody said that if you don't get Microsoft, Adobe, and Adobe in the top, then you have done something wrong. And the good thing is that I got Microsoft and Adobe up at the top here. So it seems to not be totally wrong, at least. There are so these are the usual suspects. If anybody talks about Microsoft, then it's usually a bug. But it's I'm joking, but of course it's the most effective system, and it's because of course it's the most prevalent system as well. The funny thing is you get Japanese here on top, and that's where I've speculated a bit about that. It's probably because there are some trusted sources that actually the random forest finds here that are in Japanese. So it's focusing on that. So it's you could say that that's an artifact actually. But you get some remote code execution, and of course you have to remember these are the univariate feature importance. They are not at all, doesn't say much. If you just plug in that, you don't get any risk if you get to one of these. You have to have a combination, and that's of course 2 raised to 638. That's more than the estimated number of atoms in the universe. So it's impossible to know. That's a black box. Definition of a black box, basically. You can never tell how the combination will work. Exactly what triggers what. So how we use this then? We train it on non-time data, so to speak. But actually, when we don't care about that when we do this. This is now resembling the live process here. So we have the CVs are popping in here, and then what we want to do then is to compute the score. So then we take whatever we have. If you want to compute the score at this time point, then we take a 60-day window back in time, and then take out all the features or all the entities and languages and source types, and then get that bag of terms, plug it into the predictor or the classifier, and then you get a score. And then just that continues every time. So here in the beginning, of course, we couldn't know anything about the CV number 3 and 5 because there were no information, but here we have. And then eventually when we have a confirmed exploit, we don't care about the prediction anymore because then it has happened. So hopefully in this case, we will have already predicted here, seen the signs that CV5 is going to be exploited. Now I only have 3 discrete time points here, of course, but that's being done continuously. Every time we get in a new reference, every time a new time frame or text fragment comes in, we actually then evaluate this model. So it's being done. One CVE could get like 100 evaluations one day and nothing the next day, or depending on how the references are coming in. So then to evaluate, we have the ground truth. It's the ground truth endpoint in our case is the risk rule called exploited in the wild by malware, where you got that it has been caught by a virus scan, as I talked about. Sorry, have to move around the Zoom window here sometimes, so that's why it loses the focus of the Google presentation. So and then the time point from disclosure to when you get this exploited in the wild by malware. This is the histogram of the times between that. So you see, typically you get for 2019 data, we got fairly many out of 89, actually roughly 20 for coming in the first 10 days. You actually got that verification on a technical level. And then this prediction wouldn't be of much use actually, because okay, maybe we might have triggered it in the beginning, probably would if it works well, but it's maybe not enough time in order to patch it before you got that the technical evidence. But you see that after this point, it's basically just a uniform distribution. So it could actually come anywhere. We're still getting exploit data from 2010 CVs and 2015 for the first time, I mean. So there is a hugely heavy tail, this distribution. So we can wait forever for some of the vulnerabilities. They come in so late. So it's basically they're considered. Let's say we have predicted them as then these are going to be exploited, and then we're waiting. They're false positive until we get that ground truth endpoint flagging that this was actually exploited. That is a bit of a problem because this very conservative rule, and there is no timeliness in this. So ground truth is both censored, so it's not all. It's going to get that in, and it's delayed typically. So this is a prediction score for a vulnerability from 2020. So here is before anything happened, and then you started getting references. Yes, the created that time. This is the disclosure date. Then we pop up immediately to above 0.8. So this would trigger our risk rule here, the predictive exploit risk rule, so to speak. This is our ordinary risk score, which cannot go above 80, as I said, without technical evidence. So there's no technical evidence. It seems it's really bad, everybody says, even our system, but we cannot go above. And then it drops down after a while because we have this timing out rules. And then when you get this exploited in a while, this is actually when you got the confirmation. Then this goes up. Our ordinary risk rule comes up to the top. We had already predicted here that something is going to happen, and then it falls down. So we're not interested really in what the actual value is every day. We're interested in what happened in the beginning. So you could say that it's a maximum prediction score that we've had. The reason for this going down is because we basically don't, here's the number of references per day or accumulative over day. So you see that nothing is happening here. It's basically just a few references here and there. The big bulk comes here, and that's where we're doing our prediction. Let's see. Yeah, you see here. So and this just reminding of the sliding window. So for this prediction here, it actually used all the data from this 60 days here. And for this one, you got that. And so that's why it's going down here as well, because these initial things talked about here, they're actually not present when doing that prediction. So during all this time, this was considered a false negative. Sorry, false positive, of course. And then eventually everybody said, yay, it wasn't a false positive, it was a true positive. But it's a big, it is a problem to actually get numbers on precision and recall. We've done some back calculation. We started using this in the beginning of summer, and then we have actually back predictive, going back through the beginning of 2020, doing this for all of the CVs that we have in our system from 2020, and we actually got this after tuning a bit. This is not tuning on validation data, of course, but we're trying to tune this so we get not too many false positives. And this is quite a reasonable number. It's the volume that's also important. It's not just the precision itself. So here's a precision of 0.41 and a recall of 0.41. So F1 score is 0.41. It's a good one, actually, in this case. I would say that this works, even though we're not at that level of precision of 80%. But I believe that these are not confirmed exploit. They will be exploited in the future. Not all of them, of course, but some of these. So you have the false positive, they're false positive right now, but they might come in to confirmed exploit as well. And this is the hard thing. This is probably the rule that we come up to now is probably too conservative, because we expect, this is until September 2020 for this data here. We only have 22 exploited here. Since we have roughly 100 per year exploited, we expect to have at least 60, 70. So we probably have to not be too conservative. Let's see. So now I'm gonna go through something. This is something we talked a lot about, how to estimating performance of prediction. So let's see. So assume this is very schematic. So assume you have a system that makes predictions for 5 entities at day 0. This is a prediction that's done once. We have those kind of predictions as well. So you only look once predictions. And you say, this is bad. So these are predicted bad then, red ones, and these are good. And then as time goes by, evidence comes in. So day 1, the data comes in, nothing has happened. We have no confirmation of anything being bad about these 5. So recall is not a number, precision is 0%. Really bad predictor you've created here. But day 2, it comes in here. So suddenly precision is 33%, because we said 3 and 1 got it. Recall is 100%. Wow. And then of course something comes in here, and so forth. And then eventually maybe we believe that maybe after 100 days we have gotten all the evidence. This is not what we have for the vulnerability exploits, because we have to wait basically a year in order to have some kind of clue what has been going on. But this is, you have to, when stakeholder, they are anxiously asking, what is our performance? You have to be able to get some number, but you cannot, trolla med knäna, as it's called in Swedish. You cannot just make up things. You have to have data, right? If there are no predictions, this doesn't matter to say, we have 0% precision. Yeah, but we have to wait, right? If we're in this case here. So, yeah. I guess it's nothing particular. Just keep that in mind when you do predictions. You have to have. So going straight to bullet 3 here. When evaluating performance of prediction models, you need to have a good understanding of the mechanics of the underlying endpoint, what you're trying to predict. Is there delay? Is there censoring going on? What's going on here? So you can make that. So you can do the right estimation of your performance. And it's also, you have to exercise patience in order to wait out these things and be prepared then to be able to explain this to stakeholders, that we cannot tell right now what our precision is. We will know eventually. What you can have is to get, of course, manual annotators going and say that, okay, yes, this is probably an exploit. You can do that, and maybe then before you got the technical evidence, be able to say, yes, this was a correct. It's not a false positive. It is a true positive. So what we created now is for this particular model, the reason for doing it, it was fast. It fits very well with the current architecture in our system to be able to extract these entities, and it's fast, and it actually brings value right now. But we're tuning the parameters and probably going to change the model and the feature as well, and the features used in the next couple of weeks, months or so. That's all I had. Thank you for listening.
Thank you, Matt. So we have a question from Jesper, and I think you touched upon this in the middle, but you could elaborate a bit maybe. So do you see any difference in the volume of events in relation to patch Tuesdays or other similar release cycles? So in other words, do hackers communicate more when the patches are released?
Yes, that's the only case where we would find it, actually. That's also the case. Since we're actually looking for this entity for that CVE number, so we wouldn't, probably it would be a very nice work from the, you know, if we would have known a month before patch Tuesday that we're talking about a particular vulnerability, we couldn't know that because we didn't have that identifier. So that's of course a problem with this. They have to talk about that CVE number in order for us to be able to tag this, that they're talking about this right now. They are mentioning those CVEs, and I would say that dark web, and so it's not typically that you see these kind of things. Is they are actually an exception that you see somebody selling an exploit kit for that uses a particular CVE, and please send in money to this Bitcoin account. That is not very often that I see that. It's more, you know, it's a lot of researchers doing. When you get a vulnerability, you get a lot of exploit code going out on GitHub. That's basically what you get. Everybody's trying to, oh look, I have an exploiter for this vulnerability. Sometimes that is very special. You have to special access in order to use a vulnerability. You have to be on the system and being a super user, for example. And then, you know, what's really the, you know, there is not a big risk of this being exploited in the wild, so to speak. There might exist exploit code, but it's not. So of course we want to know when they're talking about. I haven't seen a pattern like you asked for that at this. You know, you see a lot of talk about that because it's basically it goes. There are quite few that actually mentions that in that way. I'm going to exploit this vulnerability, so to speak. It's more of that we're capturing what's being said in the general community, basically.
We have a question from Pontus as well. How do you filter out the effect of your own published findings? So yeah, do you see an effect on the incoming data?
No, this is the good. We're the good phase here. We have a dark launch, so nobody can use this. So, but it's a very big, very good question. So actually now, since this is only a dark launch, actually now we're only using this internally and validating, and we could write notes then that, okay, this is a bad one. But of course, then that is going to be fed in. And if we're going to say that, okay, this is high risk, and then you're going to get those references coming in. So we basically have to shut it down, so to speak, when we have that. So we're weather prediction going on every day. We could shut it down when, you know, we don't have to predict anymore if we believe that this is so credible that this has been exploited already. And actually right now we're proposing to use the maximum score, so it wouldn't matter much anyway. It's only those if we would have something that we're not issuing a warning of, but they are still talking about it. We could get spoofed, of course. If somebody could test how can we spoof the system and talk about on GitHub various things and then see if our risk score goes up and so. So bringing actually negatives into the positive or the false positive.
Thank you, Mats, and thank you, Josefin. And thanks everyone for joining. Really nice seeing you all here today. And then before we end, just a reminder about the upcoming GAIA conference on November 27th. We are opening the registrations on Tuesday next week. So yeah, see you in November. Bye-bye.
Bye.